Okay, welcome everyone to my talk about C++ attributes. My talk is pretty much going to be consist of two parts. First of all, I'm going to talk about attributes that already exist in the language and in the compilers, and then I'm going to talk a little bit about how to create your own attributes and how to use them, for example, for additional code checking in your code base, for example. So first of all, what are attributes? I think we're pretty much self-explanatory. They're machine-readable code annotations or comments that you can add to your code, and the compiler can read it and do actions on it. Syntax, I'm aware of 4 different popular ways of writing attributes. Well, no, 5 actually. So these are the most popular ones. The GCC syntax is with the underscore attribute. You might want to add a second pair of attributes right here after the attribute, but you don't have to. Microsoft uses underscore decklspec. And in C++11, we got a standard way of writing attributes with the double square brackets. Technically, I guess pragmas also kind of count as some form of attributes, but I didn't cover it here. Yeah, so in standard C++, as I said before, we just got attributes in C++11, and the idea still is that these are entirely optional. So even if your compiler doesn't support attributes at all, it should still be able to produce a valid executable. This is obviously far from true for all the compiler extensions that can enable through the compiler-specific attributes. But yeah, in C++11, it started out with pretty much 2 attributes. The first one is no return, and is pretty much well known, I think. So with no return, you can say that your function never exits. So your function never returns, and this, for example, you might want to attach to something that has an endless infinite loop, event loop, something like that, and never ends until you pull the plug out. There's an interesting one called carriers dependency that nobody uses, including the compiler vendors. So carriers dependency says that if you, for example, have an atomic pointer and read from that pointer without a memory fence, you can attach that attribute and say, don't insert an implicit fence after the end of the function. I've tested it in a compiler explorer. So on x86, this would be completely useless anyways because they have stronger memory ordering guarantees, so they would generate the same code anyways. But in other architectures like PowerPC and ARM, ARMv7, ARMv8, the compiler might generate more efficient code with that, but all compilers I tested don't. So I think it's useless. Interesting thing to note, you can have multiple attributes in the same pair of brackets. So if you want to use more than one attribute, you can have slightly more concise syntax. In C++14, we got deprecated. We can you can just write deprecated. You can also write deprecated with a message, and the compiler usually prints out that message on the warning. And in C++17, we got a lot more. So first of all, in C++17, we got a new way of we got a bit new syntax here, the namespaces. So if you have namespaces, you can have namespaces for attributes, and then you can say user GNU, known line, and deprecated, and it was used the known line and deprecated attribute from the GNU namespace. Then no discard is also new, so the compiler is allowed to warn if you don't use the return value of your function. And with maybe unused, you can say that that the parameter that you have written might not be used. Also very important, only in C++17, unknown attributes must be ignored now. In C++11 and 14, the compiler is allowed to diagnose on attributes it does not recognize. So even if you use C11 syntax, you technically still need to have guard macros around your attributes until C17. And in 20, a big one, contracts. Because contracts are implemented on top of attributes. I think there are 3 different ones. So expects, ensures, and assert. With expects, we can set up our preconditions. With ensures, we can set up our postconditions. And assert is just a better way of writing asserts. Additionally, we will also get branch condition attributes. So with unlikely, unlikely, we can influence the code generation for branches. So in your hot code, this might lead to slightly more efficient branch prediction. No unique address is interesting because it allows you to have struct members with 0 bytes. That's interesting if you, for example, have structs that only contain functions and you just want to basically namespace your functions, then you might want to have no unique address. I believe it also makes the implementation of the tuple a bit more efficient, compile time-wise. Yes?
So a question about you said at the start the attributes were intended to be such that if you ignored them, they didn't have any semantic difference. Like you could go ahead and compile an executable and it would work. But for no unique address, like that FixIt API, so is that still the design behind attributes, or?
Yeah.
Sorry.
Well, I didn't make the decision. I like that attribute. I'm glad they made it in. But
yeah, I love it. It's great. But,
yeah. I think it's saying goodbye to that philosophy that you don't actually need these attributes. Although sometimes it still comes up. For example, something like uninitialized was also rejected on that stance. And yeah, Chris.
I was just going to agree with Simon. I thought of the same thing when you were talking about contracts. If we were to ignore the contract, then so if you were to ignore the contract and the code is to go through, then it could be problematic, couldn't it?
I think you can ignore the contract attributes simply because, well, if you do rely on side effects that you have inside of your code, inside of the contract, it's just like the assert macro today. It's just don't do it.
Okay.
It's undefined behavior, probably. Okay, any more questions so far? Okay. So there's also an interesting set of non-standard attributes that the compiler vendors have added. So first of all, syntax, because I still see the GNU syntax a lot of time. There's actually a more concise way of writing your attributes with the C11 syntax. You don't need to write the underscore attribute with the extra pair of parentheses around it. You can just say GNU visibility, for example, or Clang packed. In the case of Clang, it often understands both the GNU namespace and the Clang namespace, but this is not always guaranteed. So you need to look it up inside of the documentation. We will see in a second why this is the case. Also, it does not include MSVC because I believe one of the compiler vendors have said they don't want to have these behavioral change attributes inside of C11 syntax. And you want to use DeckelSpec exclusively for them and only introduce C11 syntax attributes for things that really don't affect your code. So yeah, different philosophy. So here's one use case for an interesting attribute. So there's a function in the Pthread library that allows you to set the name of your threads. That's very useful for debugging. For example, if you have a lot of threads and now your application crashes and you need to track down which thread did what. And then you do info threads and then you just see numbers, and that's not really useful. So I'd like to have names like that. I have my main thread here with the name of my application, then I have a thread pool of 4 threads, and then I have a scheduler thread. And there's an API that allows you to set these names. By the way, in terms of C++ updates, there was a GDB update recently that added syntax highlighting to it. So if you're using text mode GDB, you have some C++ syntax highlighting now. I recommend upgrading. Yeah, so that's the API. Pthread set name and p. On Windows, there's something similar called set thread description. Interestingly enough, the Pthread function has a restriction, and that the name of this thread may not exceed 16 characters. So oftentimes the name of the thread is known at compile time. So it would be useful to have a warning. Unfortunately, we can't use something like static assert for that, or only with a bit of pain. But there's an attribute called Diagnostics in Clang. And with that, you can evaluate constant expressions on top of these regular function declarations. And then if the condition is true or false, it will either emit a warning or an error. You can decide what you want to do. And here I just implemented a const expert version of string length, and then I pass in the pointer here, and if it is evaluatable at compile time, Clang will do so. And if it evaluates it true, it will trigger a compile time error. So this doesn't prevent you from calling this function at runtime with unknown values. But if you have a string literal, for example, you can just pass it in, and the compiler will error out if you do something wrong. Next thing, pure and const. Right. So let's assume we have a function like that, just f, that takes an int. And then we have these three functions here. A normal function that takes an int, that returns an int, and then a pure function and a constant function that also take an int and return an int. If you look at the assembly output, the function normal is called twice in the C++ code, and it's called twice in the assembly code, because we don't know what it does. For all it matters, it could be printf. It also might cause side effects of all sorts. With the attribute pure, you can say that the function does not have any internal state. So whenever you call it with the same parameters, the result will only depend on the input parameter and the global variables. So if I change this here from normal to pure, you can see that it's optimized out because it said, okay, it didn't cause any side effects. I'll just call pure once, and then add the results together. So we just eliminated the entire function call. However, the difference between pure and const is that pure might depend on global variables. So if I modify some global state here, the optimization will disappear again, and I have two calls to pure again. But I have even stronger guarantees if I use constant functions. And now it's just a single call again. So in many cases, you might want to attach those attributes to optimize the generation of your code and optimize out a bunch of function calls. Yes?
So what would happen if you violate what the attribute is saying? So for example, in the pure function, if you were calling a, I don't know, a random number generator.
If you store...
And then returning the value.
Well, you're telling the compiler that you are guaranteeing this. If you violate this contract, then yeah, well, undefined behavior.
That's what that would do.
Yeah. So the compiler doesn't check that. It's just you're saying that I ensure that this is the case. Okay. Microsoft record layout. So for those that aren't aware, the Microsoft compiler has been API stable since Visual Studio 2015 by now. It doesn't change in 19, right?
Yeah, it's the same.
Yeah. Yeah, so this obviously comes with a price, that if you do find optimizations after you've declared it API stable, you can't just simply roll them out. And one of these examples, there are a few of those examples. One of those, okay, that's not really an example of that, but it's just in general optimization. But here, no vtable allows you to stop generating vtables for certain polymorphic classes. So let's assume you have a polymorphic class with a polymorphic function, and you are certain that you never create a pointer to this type. So you actually don't really need a vtable for this type. The compiler will obviously generate one by default. This will lead to increased code size, for example. But if you are really sure that you don't need it, you can attach the declspec no vtable. And if you still try to do it, you will get a crash, but you will get smaller code. The record layout is one of these examples where they couldn't upgrade the ABI. So for example, there's a thing in C++ called empty base class optimization. If you have a class with 0 data members and inherit from it, the compiler is allowed to give it a size of 0. Unfortunately, in some cases, the Microsoft compiler cannot optimize the size out, and then, for example, the struct derived here, which inherits from 2 empty base classes, suddenly has a size of 2 instead of 1. However, if we attach the declspec empty bases attribute, it will have a size of 1 again. So if you do something like template metaprogramming and, for example, implement your own tuple class, I think that's where it's useful. You might want to use the declspec empty bases to decrease the size of your class. In Clang, there's a warning called WSwitch, and that warning triggers whenever you try to check for an enum value that is not declared inside of your enum declaration here. So this is problematic if you do something like one-hot encoding where you just want to check for certain bits and you might have different combination of your bits. So something like this case 2 here might actually be valid because it's just, no, this case 3 might actually be valid because it's just B or C, or bit and C. So this warning is a bit useless in that case. We can stop Clang from warning in these cases by attaching the Clang flag enum attribute and say, this enum just contains a bunch of flags. My possible values are pretty much all the bits you can set to 1. Everything from 0 to the maximum amount of bits that are taken. And then here it stops to 1 because 3 is actually B, bit, and C. That's a really, yes.
I was going to ask, would that still warn if you use the value, if you had a case for a value you couldn't bitwise all those?
I looked at the implementation, I believe so, yes.
So it will still warn? Yes,
because implemented by simply looking at all the bits that might be taken, and then you just set everything to 1, that's the maximum value that it can take. Yeah. Function multiversioning. So GCC and Clang have this feature that allow you to compile the very same function for different instruction set features. For example, if you have math-heavy code and would like to leverage optimizations in newer Intel CPUs or newer AMD CPUs that have wider SIMD lanes or maybe have more efficient instruction for certain operations. So if you want to use AVX2 or FMA instructions and so on, you are usually left with the choice of either excluding a lot of users or making your code slow. However, with function multiversioning, you can say compile the function for, say, the Haswell CPU, compile it for Skylake, and compile it for generic 64-bit. And then it would end up, your binary would end up with 3 different functions, and the dynamic linker on at startup will check your CPU, load the appropriate function, and then would execute the correct function with, after setup, no runtime overhead. So you might want to check out the Clang CPU-specific attribute. There's a similar one for GCC. This is, for example, used with heavy use of scripting in the Clear Linux distribution, if anyone has heard of that. So Clear Linux is a Linux distribution by Intel, that automatically attach this attribute to a large set of C and C++ code bases, and this way they do achieve a much higher performance on their CPUs because they can optimize it for much newer CPUs, even though it's able to run on older CPUs. So the binary sizes are much larger, but the actual performance is much better. Yes?
So like normally you would solve this by like having different implementation files, right? Compiling them and then linking to the appropriate one depending on what you're building for. What's the benefit of this? Just that you get to put them all in the same file?
I guess it's less typing, first of all. Secondly, you do this dynamic dispatch on it yourself, so there's some runtime overhead involved.
Okay.
This is resolved by the dynamic loader. So when you launch executable, it's when it loads a shared object, it resolves the symbols of your function, then it would check the CPU architecture and load the appropriate function. So there's no runtime overhead after that. Inlining, I think everyone has heard of that, or most people. If you use the C++ inline keyword, it is actually a hint, as Simon pointed out in one of those blog posts. There are, however, attributes to force the inlining or force stop the inlining. So there's GNU no inline, GNU always inline, and Clang has an additional one called flatten that also applies to all the function calls inside of the function itself. Which is, for example, useful on GPUs where you don't really want to do any function calls. You just say Clang flatten at the top, and everything is inlined as well as possible. Yeah, so that's only an overview of a bunch of attributes I found interesting. You should really check out the docs, especially the Clang ones are very accessible. They have a nice table of which syntax is available for which attribute, a nice, oftentimes an example, and a short description of what it does. So yeah, any questions on these attributes? Okay, so, okay.
You mentioned creating.
Yes. Yep. So far we've only looked at existing attributes. Now let's create our own one. I'm using Clang here because, as I said before, doing it in GCC is probably madness. Unfortunately, there is no simple way of creating your own attributes out of tree, so you have to fork Clang. There is a way in that you can parse the tokens yourself, but that's not a simple approach anymore. So we're not going to do that. If you want to do this, there are libraries. There is CVP-AST by Fu Nathan, and there's TinyRefl by Manu Sanchez. TinyRefl especially has a lot of, well, as the name says, it's a reflection library. You should really check it out. It's, yeah, if you want to use reflection today, use this library. But yeah, we're going to look at how to modify Clang. So here's one motivation. So I'm working on Sickle, which is basically C++ on GPUs. And if you want to run code on GPUs, that comes with certain restrictions. For example, I cannot do memory allocation. I cannot do throw exceptions. I can't do virtual function calls. I don't have recursion, stuff like that. So that's an excerpt from the specification. So today I'm looking at this one in particular. Exception handling cannot be used inside a Sickle kernel or any code called from the kernel, but of course NoExcept is allowed. So the way Sickle is structured, we compile regular C++, and therefore we don't really know. If you look at the function themselves, you don't really know if it's run on the CPU or the GPU. But maybe you want to have some static check that ensures that you can easily port your code to the GPU later on. But first of all, I'm going to do a small detour on explaining what I'm actually going to do. So inside of Clang, there's a tool called TableGen, and TableGen is a code generator inside of LLVM that allows you to describe domain-specific information about all kinds of things. It's used, for example, to describe the instruction sets of different CPUs. It's described to it's using for describing all the attributes that are available in Clang. It's used for generating all the code for the different diagnostics that can print out. So it's used for all kinds of things. And this is an example TableGen file. I heavily stripped it down. So that's basically a stripped down version of the attribute TableGen file, where there's a class called spelling. Here you can see where the GNU and the decalspec comes from, for example. And yeah, it's basically just boilerplate. The thing is, TableGen has different backends, and these backends are written in C++, so it's not really a generic code generator, so to speak. That's why the syntax is very, very specific in this case. And also, the things that you can write are also very, very specific, like all these bits. Yeah, and here's an example definition of an attribute called address space. The address space attribute is only available with the GNU spelling. It takes an integer as an argument, and it's undocumented. And if you run this through TableGen, you may end up with this file. So if I call it with gen clang attribute classes, it will generate the C++ class declarations for me. It's probably something you could write by hand, maybe except for the more specialized RTCI that LLVM uses. However, TableGen can do more. For example, if I call it with gen clang attribute parse attribute kinds, it will generate some parsing bits for me. For example, it will look inside of a token. It will look for the address space string with a mem copy. There are also different generators. For example, if you want to check out if you have an attribute and want to know which one it is, it can also define or generate an X macro file that the hash include, and it's had some defines before and some defines after. And then it would just generate a giant switch case with hundreds of different cases. But yeah, so we're going to use this to define our own attribute. All the attributes are defined in include/clang/basic/attributes.td. And all you need to do is you write this. You write def, the name of your attribute, which is an inheritable attribute. I want to have C++11 spelling instead of the CPP Edinburgh namespace, and want to call this attribute GPU_friendly. I want to attach it to functions only. So if I try to attach it to, say, a namespace, Clang would automatically give me an error. I don't need to write the boilerplate for it. Yes, Chris?
Do you put this in attribute.td or in GPUfriendly.td?
In attribute.td.
Okay, so it's just one file.
It's one giant file. Okay. Yeah, inheritable attributes mean that this attribute is inherited by redeclaration. So I can forward declare a function, and if I forward declare this function again without this attribute, the attribute is still in place. And with that, we have already created our own attribute. So if I do this, cpp ed GPU friendly, and some function that just adds one integer to another one, I get nothing. So this is the generated AST. Here is the beginning of my translation unit. This is just a bunch of built-in data types, and here's my function declaration. I have 2 parameters, and this is the body of my function where I have the union operator and no attribute attached. And the reason is that we just defined the parsing, but we didn't attach any semantics to it. So Clang doesn't know what to do with this attribute. So let's do this. In fact, if you try to run it like that, you get a nice assertion error and it fails, saying that you didn't handle this attribute. So let's add semantics. In this file, Clang just told us where it crashed, so let's go to this file. And inside of there's a function called process_decl attribute with a giant switch case of every attribute. And there you add your own case here with pass attribute : AT GPU friendly, which is what you had in a TableGen file. And in the usual case, you would just call a function called handle GPU friendly attribute and break. And then the handling of your function, of your attribute, is in the end most likely going to be handle simple attribute. So right now we're just doing nothing with this attribute, we're just saying handle it. And if we do this, we can see it here attached to our function declaration. So now we have it available in the AST and we can work with it. So now that we have it in place, we can start to add some checks to it. For example, it doesn't make sense for the GPU-friendly attribute to be attached to the main function. We can't just run a main function on the GPU. So let's add a check for it. If it's main, let's yell at the developer and then continue the handling. This would most likely look like this. So one way of doing it is with ad hoc diagnostics. You get the AST context, then you get the location of your declaration, and then you're saying, I want to print a diagnostic. It doesn't exist in Clang, so please give me an ID for a new one. Here is my error message: main cannot run on GPUs, and please report it at the location of the function declaration. This also works out of tree, by the way. So whenever you want to write a Clang tool or want to create an error, this would be one way of doing it. You don't need to fork Clang to add your own diagnostics. And if you actually run this, you get a nice error here. So error, main cannot run on GPUs at this location here with this caret here. However, we already forked Clang, so we might as well just add it in tree, so we have a bit of more features. For this, we go to basic/diagnostics-cmykinds.td, where we attach our own the definition of our own error message here. Here we're saying some function cannot be run on a GPU, and it's an error. And then we slightly change the handling in CMA and say, I want to print out a diagnostic with this diagnostic I just defined in the TableGen file. I pipe in the name because it's parameterized now, and let's add the source range, so the entire range of my function. So it would also generate these small little this range around my function declaration. Another warning we can implement is we can suggest NoExcept, because as I said, we cannot throw exceptions on a GPU. So on the function itself where we attach the attribute, if it doesn't have NoExcept, we might as well suggest adding it, because otherwise this attribute wouldn't make any sense. So let's add it as a warning. In fact, I wrote error here. It should be a warning where I say function is marked for execution on GPU, consider making it NoExcept. And then we just add a small if to that handling here. So first we check, do we have a function prototype available? If so, let's check the exception specification. If it does not have an exception specification, so it did not use NoExcept or the empty throw, we emit the warning with the same source range. We can go in further and try to automatically fix it. So here I'm just saying, okay, in the case the developer should attach the NoExcept, I'm getting the the location of the end closing parenthesis and go one step further. So I get my function type location, I get the right parenthesis with an offset of 1, so 1 to the right, and then I tell Clang to create a FixIt hint where I just want to insert the NoExcept string at that location, and then I attach it to my diagnostic. I should also add that I'm cutting a lot of corners here. You should do your error checking properly. I guess this would crash in many cases. But this is just to give you an idea of how you would actually approach it. And if you do this, so let's switch here. So yeah, so that's the code from, wait. So that's my code, cpp add, GPU friendly, void f. I print the AST out. Here's my attribute. And here it says, f is marked for execution on GPU, consider making a NoExcept. Here is the caret with the range, and here it already suggests NoExcept. And if I want, I can also tell Clang to automatically fix it for me. So just say xclang dash fixit. Note, fixit applied, suggested code changes, one warning generated, and if I cut it again, here it is. I can, while I'm at it, I might as well just add a main function. And main, run it again. And here I have my error. Main cannot be run on a GPU. And I can apparently can consider making a NoExcept. Okay. So, not shown. Whoops. I didn't show the AST visitors or the AST matches which are available in Clang, which is a much higher level. So the AST matches are a much higher level API of accessing the AST, which you could use out of tree. We don't need to fork Clang for that. The AST visitors, just the same, just slightly more lower level, and they give you more control about how to iterate over the AST. Likewise, recursive checking, because as I said, I should actually check the NoExcept on the top function and on every function call, but I didn't do this in the small example. Also, you might consider moving it to Clang tidy instead if you can afford it. So you might as well just only add the attribute to your fork of Clang and then move the actual check to Clang tidy, because that's where all the checks and the fixit usually belong. And there's a very handy tool that is a part of Clang that is called Clang Query. You can open it in the browser. So that's a fork of Compiler Explorer, and it will soon be added to regular Compiler Explorer as far as I know. And that has Clang Query added as a tool. So here's the regular old Compiler Explorer example with a square function. And now I want to look where I want to match all function declarations, for example, in my code base. So all I type into Clang Query is m format function decl. And then it would look up past the C++ code and look up all the declarations in the code. And you can do it with very, very complicated AST matches and do extensive analysis or source code like that. So when grep doesn't cut it anymore, you might want to look at Clang Query, which is usually shipped as part of Clang Tools Extra. And with that, I am at the end of my talk. So this would be, what I've just shown you would be one way of improving the quality of your source code by just adding the domain-specific warnings to your own compiler. So one might want to take a look. If any questions? Yes, Joe.
So last time I tried to mess about with the source code of Clang, I was mostly doing backend stuff, but I found it really hard to figure out the API. Like the documentation was really difficult to find, or it didn't exist, or whatever. So how did you, like all those functions you were calling to look at the AST, how did you figure that all out?
So all the hooking up into the AST and so on, it's basically just copy paste. So
like other attributes.
Yeah,
okay.
Because once you have found the attribute.td, it's pretty much straightforward. You copy paste whatever you found in that TD file, then you get this assertion where it already tells you where you need to go next, and then you implement it there, and then you have it. The rest of how do I query the information of my AST nodes, so does this function declaration, is this main or is this NoExcept and so on, I just use the DoxyGen that is available online. It's not too bad because you already know the type. So my process usually is I look at the AST, and there's already the name of the class, and then all I need to do is check out the documentation of the class, which has a bunch of methods defined.
Okay.
Yeah. Also, IDEs help. So don't just use VI without any plugins or something like that. Any other questions? Okay, I guess we're done.